Alternating current fundamentals. Number 2. Electrical generators and motors.
In the last video, the principles of magnetism were examined. You saw how unlike magnetic poles attract, while like poles repel. The important link between magnetism and electricity was demonstrated. You saw that a current-carrying conductor creates a magnetic field when connected to a DC source. In this video, basic principles of current and voltage will be reviewed. You'll be introduced to some alternating current concepts. A simple generator will be used to produce alternating current. You'll see how electric motors run on alternating current. Let's get started by reviewing some electrical principles at the atomic level.
Electrons are the particles orbiting the nucleus of an atom. Each carries a negative electrical charge. In certain elements, some of the electrons are only loosely bound to their atoms. When subjected to a force, such as voltage, they can be dislodged from their parent atom. They are then free to move from one atom to another. These are referred to as free electrons. Current can be thought of as the impulse transferred from one free electron to the next. This impulse travels close to 186,000 miles per second, the speed of light.
The electrons themselves do not travel through the wire at that speed, but the repelling and attracting effect causes the current to do so.
In electricity, the terms positive and negative are used to describe a difference in potential. If a material has extra electrons, it's said to have a negative potential. If it has a shortage or deficiency of electrons, it's said to have a positive potential.
Here's an important current law. Electron current always flows from an area where there's an excess of electrons to an area lacking in electrons. In other words, electron current travels from a negative potential to a positive potential.
The term voltage is used to describe this difference in electrical potential. Voltage can be thought of as an electrical pressure. The current flows as long as the difference of potential, or voltage, is present. The voltage causes the current to flow through the conductor. In some circuits, the current always flows in one direction, from negative to positive. You already know this to be direct current, or DC.
But there's another type of current that doesn't always flow in the same direction. This is called alternating current, or AC. An AC voltage source is indicated by this symbol, which you'll learn more about in the next video. As its name implies, this type of current alternates, flowing first in one direction, then reversing and flowing in the opposite direction. It's important to realize, however, that alternating current still flows from negative potential to positive. It is the polarity of the power source that alternates. Polarity is the property of an electric charge that refers to either a deficiency of electrons, designated by a plus sign, or a surplus of electrons, designated by a minus sign.
When the polarity of the source changes, the current changes direction. When this happens, you might think that anything it would accomplish while flowing in one direction would be undone while flowing in the opposite direction. But most transducers, which are devices that change one form of energy into another, need only to have a current flow through them regardless of direction.
For example, current through the filament of a light bulb causes it to incandesce due to the resistance of the filament. Changing the direction of current flowing through the filament will not affect its resistance. Therefore, the lamp continues to light. As another example, a heating element will heat on both AC and DC. The movement of the electrons through a resistance will produce heat, whether flowing continuously, as in DC, or changing direction, as in AC.
Basically, alternating current can do everything that direct current can, and more. AC has two important advantages over DC.
One advantage is that AC can be more cost-effective to transmit over long distances. A second advantage is that AC can be transformed to different voltage and current levels, allowing it to meet the needs of many different components in circuitry. Because of its changing direction, an AC voltage can be more easily increased or stepped up for transmission, as happens to the voltage being distributed from a power plant. Likewise, it can be decreased or stepped down before it reaches its destination, such as your home. While a conductive wire is thought of as having almost no resistance, It does have some resistance over miles and miles of wire. This cumulative resistance is enough to cause a voltage drop over the resistance of the wire itself.
Let's look at a mathematical example which compares the power loss of AC and DC during transmission.
Use the power formula I equals P divided by E. If a DC voltage of 100 volts were used, then when the power demand was 1,000 watts, it would require a current of 1,000 divided by 100, or 10 amps in the power line. Assume that 100 miles of power line has 10 ohms of resistance. Since the power line has 10 ohms resistance and power equals current squared times resistance, the power loss, just in the power line, would be P equals 10 amps squared times 10 ohms, or 100 times 10, which is 1,000 watts. This means that the source would have to supply 2,000 watts to get 1,000 watts to the destination.
This would be a significant waste of energy used up in the power lines in the form of heat. However, if AC is used, it can be stepped up from 100 volts to 10,000 volts AC, for example.
Now, for the same power demands as given in the previous example of 1,000 watts, the required current would be 1,000 watts divided by 10,000, or 0.1 amp. Using the same 10 ohms of resistance, the power now lost in the line is P equals 10 times 0.1 squared, which is 10 times 0.01, or a tenth of a watt lost by using AC. Now the source need only supply 1,000.1 watts to transmit 1,000 watts to its destination.
From this example, you can see the enormous amount of energy saved by using AC to transmit electrical power rather than DC. Most electrical energy generated for public use is alternating current. The production of AC relies on the relationship between magnetism and electricity. Let's see how.
In the last part, you saw that magnetism and electricity are closely linked. Using iron filings, you saw how an electric current passing through a conductor creates a magnetic field around it. This is electromagnetism. But the reverse is also true. Magnetism can induce a current flow.
But before doing a demonstration, let's consider some important safety requirements. Since the human body is able to conduct electric current, you must make sure you are properly insulated from any conductive paths. Here are some personal precautions.
Never wear jewelry or any sort of metal when working near electric current.
Always wear some form of eye protection.
There is no special clothing requirement for electronics technicians other than common sense. No loose clothing that can get caught in the moving parts of an electromechanical device, for example.
Here are some precautions for equipment. Never use frayed or cracked cords.
Only use tools that are properly insulated.
Consider all wires hot.
Remember, safety always comes first. Now let's demonstrate how magnetism can produce electricity.
This can be done by using a horseshoe magnet, which has a north and a south pole and a magnetic field between them. A length of copper wire is used as a conductor and is connected to a zero-center microammeter. Look at the meter. Notice that the pointer rests on 0 at the center of the scale. Watch what happens as the conductor is passed downward through the magnetic field. The pointer moves to the right, indicating a current flow in one direction. Now the wire is passed through the magnetic field again. This time it's passed upward, cutting the magnetic field in the opposite direction. Notice the pointer now moves to the left of center, indicating a current flow in the opposite direction.
This simple demonstration reveals the basis for the production of AC electricity. A wire cutting the magnetic field produced current in one direction. But moving the conductor back the other way through the magnetic field caused current to flow in the opposite direction.
Current flows in this circuit because the movement of the wire through the stationary magnetic field causes a voltage to be induced within the conductor.
Let's try a different approach. This time, the wire will be in a fixed position.
The magnet is passed near it in an upward direction. Notice that the meter indicates that a voltage is induced. So it doesn't matter whether the magnetic field is passed over the stationary wire or the conductor is moved through a stationary magnetic field. Both actions will induce a current to flow through the wire.
This process is called electromagnetic induction and is the principle behind the generation of AC electricity. In order for it to occur, either the conductor must move or the magnetic field must move. The voltage generated in the conductor is called an induced voltage. Using a length of insulated wire for demonstration purposes, let's look at 4 factors that affect the induced voltage.
One is the strength of the magnetic field. The stronger the magnetic field, the greater the induced voltage will be.
Another factor is the speed at which the conductor or the magnetic field is moving relative to the other. The faster the speed, the greater the induced voltage will be.
Another factor is the angle at which the magnetic field is cut. The more perpendicular the angle, the greater the induced voltage will be.
And a final factor is the length of the conductor within the magnetic field. The longer the length of the conductor moving through the magnetic field, the greater the induced voltage will be.
These 4 factors are related to a basic law of electromagnetic induction, known as Faraday's law. This law states that the voltage induced in a conductor is directly proportional to the speed at which the conductor cuts the magnetic lines of force. This law is the basis for the design of the electric generators in use today. Let's take a closer look at how a generator works.
Generators are one of the most common sources of electrical energy in the United States. As an example, a gas-driven electric generator may be used on a construction site or on a pleasure boat to provide the same kind of electricity used in the home. An electric generator is a mechanical device that converts mechanical energy into electrical energy. The mechanical energy can be provided in different ways. Generators may be powered by the wind. There are many places in the United States where wind-driven generators, each connected to a large windmill-type blade, are used to create electrical power. Electric generators may also be powered by water. These are located at dams, which form artificial lakes. Water flowing down through tunnels in the dam toward rivers produces the energy needed to rotate large turbines, which in turn provide mechanical energy to several generators located within the dam.
In order to better understand how AC current is produced, let's look at a highly simplified version of an electric generator.
It's made up of a coil that revolves between the poles of a horseshoe magnet. Notice that the coil has been colored green at one end and yellow at the other to keep track of their position during rotation.
Let's slow one revolution of the coil way down to see how it interacts with the magnetic field through which it's traveling. Although it'll be stopped in certain positions, you must remember that in order to generate AC, the coil is constantly spinning.
As the coil revolves through the magnetic field created by the 2 magnetic poles, it cuts through the flux lines at different angles. To start, the coil rotates to a horizontal position with yellow on the left and green on the right. This graphic shows that for this instant, the coil is positioned parallel to the magnetic lines of force as represented by the arrows. At this point, no voltage is induced because the magnetic field is not being cut. But now, as the coil moves clockwise, it cuts through the flux lines at an increasing rate. At the instant that it reaches a vertical position, the coil is perpendicular to the magnetic field, which means that it's cutting the maximum number of flux lines. Here, the voltage induced by the generator is at a maximum. As the coil rotates further, it moves back into a horizontal position. As it does, the coil cuts fewer and fewer flux lines. Once again, when the coil reaches a position that is parallel to the magnetic lines of force, no voltage is induced because, for this instant, no flux lines are being cut. But notice at this point that the coil has rotated 180 degrees, or a half circle, from where it started. Now the yellow end is on the right and the green on the left. It's important to realize that proceeding from this point in the rotation, the yellow end of the coil will now be cutting the magnetic field in the opposite direction. From an earlier demonstration, you'll remember that when the magnetic field was cut in the opposite direction, a voltage of an opposite polarity was induced. It's this principle of AC generation that creates its alternating aspect, where polarities are reversed. As the coil rotates further into a vertical position, it once again cuts an increasing amount of flux lines until it reaches a point where the maximum amount of voltage is being induced. Finally, the coil rotates back to the original position where the coil is situated, parallel to the flux lines, and no voltage is induced.
This simple procedure demonstrates the fundamental principle of all AC generators.
But remember that a magnetic field surrounds the conductor in which the current is generated. This magnetic field is such that it opposes the movement of the conductor. It produces an opposing or counter-electromotive force, abbreviated CEMF. This principle is reflected in Lenz's law, which states that a counter-electromotive force has a polarity that opposes that of the source that created it. Because of this principle, it takes a great deal of power to drive a generator while it's producing current. The greater the current produced, the greater the power required to drive the generator.
Simply stated, under certain conditions, magnetism can be used to generate electricity. You've seen how generators do this relying on electromagnetic induction. Now let's consider the opposite process, how electricity produces magnetism. You know this effect as electromagnetism. The operation of electric motors is based on this process.
While you saw that an electric generator is used to convert mechanical energy into electrical energy, electric motors do just the opposite. A motor converts electrical energy into mechanical energy. There are basically two types of electric motors. One type operates on DC. This type of motor is similar to the starter in your car, which converts the electrical energy in your car's battery into the mechanical motion of starting your car engine. Small, low-torque DC motors are found in audio tape decks. An AC motor, on the other hand, is constructed to operate on alternating current. This type of motor is most commonly used in household appliances, such as air conditioners, as well as in many industrial applications to run machinery.
Now let's see how motors work. Remember, an electric motor's job is to change electrical energy into mechanical energy. Let's take a closer look.
When a current-carrying conductor is introduced into a magnetic field, the lines of flux are distorted. This is because, as you've already learned, the conductor brings a new set of flux lines with it. The conductor's flux lines circle it in a specific way depending on the direction of current flow. Remember, the left-hand rule for conductors can be used to determine the direction of the flux lines. This rule will help you to visualize the direction of flux lines around the conductor.
The key to the operation of an electric motor is found in the interaction of the two magnetic fields, the stationary field and the moving coil.
You'll remember that magnetic lines of force without any interference will follow the shortest path from the north to the south pole. However, the introduction of circular flux lines from the conductor prevents the magnetic flux lines from pursuing a straight path. This is because flux lines do not intersect.
Instead, a complicated relationship develops between the two sets of flux lines.
Because the conductor's flux lines are circular, they interact with the magnetic flux lines in opposite directions on either side of the conductor. On one side, with both sets of flux lines traveling in the same direction, they become tightly spaced and work together to create a stronger magnetic field. On the opposite side, where the two sets of flux lines run in opposing directions, they become more widely spaced and form a weaker magnetic field. The result of this difference in flux line interaction causes the conductor to be pushed by the strengthened field toward the weakened field. The magnetic push continues until the conductor leaves the field of strong flux interaction.
Magnetic push from stronger field to weaker field is used to create movement in an electric motor. Let's see how the motor is designed to convert magnetic push into a rotary motion.
An electric motor is designed to take advantage of magnetic push. The conductor inside the motor is bent into the shape of a U. It's connected to a pivoting base that allows the conductor to spin between the two magnets. This conductor is called an armature. Around the base of the armature is a split copper ring called a commutator. Outside the commutator are two brushes that slide along the commutator and provide an electrical connection for current to the armature. As the armature is supplied with current, its circular flux lines interact with the magnetic field's flux lines, as you saw earlier. The armature is designed so that the magnetic push, or torque, which results from the interaction between the two fields, causes the armature to rotate between the two opposite poles of the magnets. Because the armature is U-shaped, its flux lines change direction relative to the magnetic field flux lines on opposite sides of the armature.
To see this more clearly, let's look at a graphic representation of a side view of the armature.
The two circles represent the left and right sides of the armature. On the left, current is flowing toward you, represented by a dot in the circle. On the right, current is flowing away from you, represented by a plus inside the circle. You can think of it as the tail of an arrow as it moves away from you. Because current flows toward you on the left side, the flux lines rotate in a clockwise direction. But since current flows away from you on the right side, the flux lines rotate in a counterclockwise direction.
The alternating direction of current flow in the U-shaped armature allows the motor to put magnetic flux line interaction to work. Here's how.
On the left, the armature flux lines distort the field flux lines, and magnetic push moves the armature downward. At the same time, the armature flux lines on the right also distort the field. Here, because current is flowing in the opposite direction relative to the permanent field, flux line interaction causes the armature to be pushed upward. The U-shape of the armature creates two opposite flux line interactions that combine to push or rotate the armature within the permanent field. As the armature rotates, it becomes perpendicular to the magnetic field and enters the neutral plane where the interaction of the magnetic field is balanced. Here, there is no longer any push on the armature. At this point, the brushes cut current to the armature. However, because of the rotating motion, momentum carries the armature into the opposite field. Once there, the brushes reestablish contact with the commutator, supplying current and thus ensuring the continuous spin of the armature.
This ongoing process, current to the armature, interaction of opposing flux lines, and magnetic push on the armature is what creates movement in an electric motor. Any work that a motor performs is the direct result of this process. As you can see, the relationship between magnetism and electricity is important for both the generation and utilization of AC electricity. Let's stop here and review what you've been shown.
In this video, you saw how electricity, magnetism, and mechanical motion are related.
The fundamental principles behind electric generators and electric motors were shown.
You saw that both AC and DC can be used to convert electrical energy into mechanical energy, the function of electric motors.
You also saw that mechanical energy can be used to create AC or DC, the function of electric generators.
As you have seen, an understanding of the relationship between electricity and magnetism has helped you understand the operation of electric generators and motors. In the next video, you'll see how alternating current can be measured.